So this is part 3 of differentiability and continuity. So I want you to look at this little fact up here, because what we're going to see is that in order to take the derivative of anything, we have to make sure that it's continuous. That's going to be a criteria. And we're not going to always have really simple functions. So what we want to know is that if you make something that is the sum of continuous functions, the new function will also be continuous. So with this function right here, this is y equals x. We know that's a line. It's continuous. We know y equals the absolute value of x is a v. It's continuous. Now, we know it's not differentiable at that little corner, but it is continuous. So that tells me that this new function is also going to be continuous. Okay, so just keep that in mind, because that'll be one of the things that we have to check later on. And you're going to say, I know that this function's continuous because all of its pieces are continuous. Okay, so now we're going to look at what happens on something that is continuous but not differentiable. So I have the absolute value of x squared minus 5. And this little graph is in your packet, but I think says page 16. And I'm hoping that you guys learned in pre-calculus, like you should be able to get this graph. Like, this shouldn't be like a mystery to you. So I want you to think about the graph of x squared minus 5. So that graph would go like that, something like that. Well, if I put absolute value bars on it, I can't have any negative numbers, right? It all has to be positive. So all you do is wherever it's negative, you reflect that over the y-axis, or excuse me, x-axis, and then you get rid of that. So that's how that function looks like that. Okay, so there's debate about what makes a sharp corner and what makes a cusp. I don't want to get into that debate. So I don't care whether you call it a sharp corner or a cusp, because even the AP teachers that have been teaching forever cannot agree on that. So if you have a professor in college that's got a certain definition, then you go with their definition. For me, call them whichever one you want. Okay, so the function we're going to say is continuous from negative infinity to infinity, but not differentiable. And we specifically can see that it's not differentiable right at those two places right there. And what's happening right there is the function's equal to 0. So let's figure out, we know that x squared minus 5, let's figure out when that's going to equal 0. Well, when x squared is 5, or x is plus or minus. And notice I don't have to use the absolute value bars, because remember on our original, I mean, that's the same, right, as it was without absolute value bars. Okay, so I'm going to say that it's differentiable from negative infinity to negative square root of 5, negative square root of 5 to positive square root of 5, and 5 to positive infinity. Okay, so that's all I need to do when I can just get rid of that point. Okay, so let's see what's going to happen with piecewise functions, because a lot of things can happen in a piecewise. We could get corners on piecewise. So piecewise are a little tricky. So to know if they're differentiable, the derivatives need to be the same on either side of the x value. And the function must be connected and smooth. Okay, so let's look at an example. So I want you to find the value or values of the constant A. So all that is saying is that A is a value. It has some value. It's not a variable. Okay, so this time we want to make something differentiable. They're giving us a piecewise function, and they're saying A is going to be some value. Okay, so we said that this has to hook up, or it has to be smooth and connected. Okay, so let's start with that. So we're going to find the value of A. Oops. When x equals 3. That will ensure the pieces hook up. Okay, so if those pieces are going to hook up, well, these have to equal each other when A is 3. Okay, or excuse me, when x is 3. So I'm going to say when x is 3, I know that ax squared minus x has to equal 2a. Okay, so that's going to be 9a minus 3 is equal to 2a. So that is 7a equals 3, and a would be 3/7. Okay, so we've got that part done. We know that it's going to be connected there, but is it going to be smooth? And in order to know that it's going to be smooth, we need to have the derivatives on the left and the right have to be the same. Or, the limits. Okay, so I'm going to say the limit as x approaches 3 from the left. So as I'm coming from the left, I need to use that function. And a is 3/7. So 3/7 x squared minus x is going to be 3/7. X squared is 9 minus 3. So that is 27/7. That is 21/7. It is equal to 6/7. Okay. The limit as x approaches 3 from the right, so I'm going to use this function right here. A is 3/7. So I have 2 times 3/7, which is equal to 6/7. Okay, and you have to show this work right here when you're doing this as a proof. Okay, so I've shown it. Thus, I'm going to say that A is equal to 3/7. And I think I'll put here, I should make a conclusion. I'm going to say the limit as x approaches 3 from the left equals 6/7, which is equal to the limit as x approaches 3 from the right. Therefore, okay, so I have this from both of these pieces. I showed that it connected, and then I'm showing right here it's smooth. Okie dokie, that's it. Bye-bye.